Number 8 looks like some form of arctan. I see an x squared in the bottom, but the derivative of arctan of x is 1 over x squared plus 1. So I need to deal with these two constants. So I'm going to rewrite this and try to make the inside of the integral look as much like the form of the derivative that I'm used to for arctan of x. So the first thing that we can do is we can factor the 3 out front of the numerator. Now I need to turn this 4 into a 1. So I can do that by factoring it out of the denominator. And then it looks like this might be some kind of chain rule problem, right? Where we took the derivative of arctan of something. So I'm going to rewrite it one more time so I can get a better look at what might be inside the arctan function. So x squared over 4 is really x over 2 squared plus 1. Now I can see that this looks like it's probably going to be 3/4 arctan of x over 2 plus c, right? But just to be sure, because there was a chain rule involved, like with the last problem, I want to verify my result. So I'm going to verify my result by taking the derivative of it. And when I take the derivative of this, I get 3/4 times 1 over x over 2 squared plus 1, but then I have to take the derivative of the inside function because of this chain rule here. So if I look at my answer compared to what I started with, I have this extra 1/2 when I take the derivative, but it's gone here. So in order to make the 2 in the denominator disappear when I take the derivative, I need to multiply the numerator by 2 in my answer here. So now if I were to take the derivative of this function again, I would have an extra 2 to multiply by and make it go away. So my final answer, 2 times 3 is 6, which reduces to 3/2 arctan of x over 2 plus c. So now if I take the derivative of this, I get back this guy. 9 says solve the following differential equation. So when we looked at differentials, we said, well, all that really was taking the derivative, dy dx of a function, and then separating the dx from the dy, and we did that by just moving it to the other side of the equation. So when we solve a differential equation, it's really the same thing as saying find the original function y. So dy is 7 cosine 3x minus 4 cosecant x cotangent x dx. Now, if I take the integral of both sides, I get y on the left, and the derivative of sine is cosine, so I have 7 sine 3x, and in the same way that I needed the 1/3 on the e to the 3x problem, I'm going to need a 1/3 here, because if I try to take the derivative, I'm going to have an extra 3 come out. So I'm actually going to divide this by 3. So now if I check this, I see I would get 7 cosine of 3x times 3 over 3, and those 3's would cancel and I'd end up back where I want to be. The antiderivative of negative cosecant cotangent is cosecant, so this becomes plus 4 cosecant x. Number 10 is another initial value problem. So to solve the initial value, that's the same thing as saying, give me the function and now find the actual exact value c. So we start by integrating the derivative that we see. So this is the natural log of the absolute value of x minus x plus c. And so then we know this is this is the general solution for f of x. Now I can find the exact solution by using this data point that I was given. So f of -1 will be the natural log of +1, because the absolute value of -1 is 1, minus a -1, so it becomes a +1, plus c, and all of this should be 3. ln of 1 is 0, so I'm just going to have 1 plus c. So c equals 2. So the final answer is f of x equals the natural log of the absolute value of x minus x plus 2.